Hello again. Okay, so we're going to carry on with polymerization. This time we're looking at condensation polymerization. So this uses the condensation reaction that we've already talked about a couple of videos ago. So this also known as a step reaction, but we'll call it a condensation polymerization, condensation reaction when we refer to it. It's going to happen when we have two monomers that each of them will have some functional group that react to join together. So we saw this in the case of amino acids, where we had an amine on one side, and there's just a side group, and a carboxylic acid on the other. So we said that when we had another one show up, this could react across these two functional groups to produce water, hence the term condensation, and also a new bond forming between the double bonded oxygen and, in the case of an amino acid, and the nitrogen. So you'd end up with all of this going away as just H2O. And a new bond forming into an amide bond, right? So that's the general idea. And if we have either one monomer that has both groups, or like in our first example, we have two monomers, this would be a copolymer that can bond together, each one of them having, say we have the terephthalic acid here, where it's got two carboxylic acid groups, and an ethylene glycol that has two oxygen groups on it. So remember, that would be so the eth with the two, and then two alcohols coming off of it. Okay. Or it'd be an ethane diol, if you want to use the proper word instead of ethylene glycol. So it has two alcohol groups on it. So now this carboxylic acid can react with the alcohol, and just even as it's showing there. So that's going to split off as water. And what is left behind is this carbon bonding directly over to that oxygen, the double oxygen bond on the other carbon. So this is an ester bond. But let's take that just step by step, shall we? So showing the same method that we had, that we were talking about before in the mechanisms video. So let's draw our benzene ring, and we have two carboxylic acid groups para to on each other, right? Okay. OH. Okay. And it's going to encounter now the alcohol of CH2, okay, OH, of the ethane diol. Okay, so when we're looking at this reaction, the first thing that's we want to think about is how, where is the sources of electron density, and where are we going to have a low electron density, or relatively low? Okay, so on around all of these oxygens, remember we've got these lone pairs that are going to be a high electron density around all of those oxygens. And again here, we know that this forms or the carbonyl forms a resonance structure, because this double bond can push up onto the oxygen and we'll have a negatively charged oxygen. And again, that's why we have a pretty weak hold on that hydrogen, because a negative charge can be spread across these two things. Okay, so let's go ahead and we'll draw that first. Okay, so I'm just going to use this. I think it's pencil, actually. Ugh, it's ugly. I'm not going to use that again to show the first step. So let's, and I'm just going to call the rest of this just as R1, okay? And the rest of this, we're going to call R2, just so that I don't have to write it out each time. So we have R1 bonded onto our carboxylic acid. And before I draw that, let's just say we're going to do a first step showing the resonance, okay, of that double bond going up onto the oxygen. So we would have 1, 2, 3, 4, 5, 6, and a negative charge on the oxygen, and a positive charge now on that carbon that is at the crux of these two oxygens. Okay, and over on the other side, we still have this alcohol group. Okay, so the next step is that this alcohol group has, again, electronic density here with these lone pairs, and now there's a positive carbon, okay? So that's, remember, we're talking about a resonance structure, so it's always going to be a little bit more positively charged on that carbon than it would be on either of those oxygens. We're just going to show it explicitly here. So let's show our electron density going from where it is to where it's going to be, and that will be the new bond that we're going to make, okay? So now we're going to have R1 with a single bonded oxygen and an alcohol group here. And it's going to be bonded to the oxygen that we just drew there. And it's going to be bonded to a hydrogen as well as R2. Okay. So what's going to happen next? So from a mechanism point of view, really what we should do is think about how these electron density is going to flow here, okay? So we know that this oxygen negatively charged, and now we also have a positively charged oxygen because it's got 3 bonds on it. So that's not really going to last for very long. And this negative charge is less stable than if we drop it back down into a double bond. But we can't do that before we resolve, or at least not without simultaneously resolving what we're going to do about having 5 bonds on this carbon here. So we can either take off of one of these 2 bonds, okay? And you have to think that while this is happening in solution, both of these options are going to happen. Just one of them is going to produce a more stable product over time that will accumulate, okay? So if we drop these lone pairs back down into a double bond, and we then take this bond off and return it to that oxygen, okay, that's just back where we started. So yeah, that is an option, and it's completely legitimate, except it doesn't move us any further in the reaction. Okay, so instead of that bond dropping off, let's push this bond onto the hydroxy group, okay? And we'll carry on drawing over here, just so that we can keep going right to left, okay? So this is going to go off page and carry on down below. So now we have R1, okay, onto, again, a double bonded oxygen. So we just drew in that second bond again, bonded to the oxygen, and R2, but it still has its hydrogen bond on there. And we've also created now a hydroxide, right? Because we just dropped off this alcohol group by itself is a hydroxide ion, which we know can be stable in water. Okay, so now we've got the oxygen's lone pairs are there. This is going to be the positive charge still on that oxygen. And now we have the negative charge on the hydroxide. So we haven't changed the overall charge anywhere. Everywhere has always had either neutral or 1 positive, 1 negative. We can't drop charges anywhere. So now the last step is how are we going to stabilize this positive charge? So really what's going to happen is the electrons on this hydrogen, the oxygen is going to draw them towards itself. So that'll resolve its positive charge. And the negative charge on the hydroxide is going to come and pick up and make a bond now with that hydrogen. Okay, let's do that slightly differently just so that we can see it. Okay. So we're going to say that this is going to now form a bond with that hydrogen, okay? So take it for our last step. We've got R1 into a double bonded oxygen, down through the other oxygen onto R2, and we also have created water. Okay, so that's it. That's the new bond going across these two starting molecules, and that makes an ester as a functional group, and that's the condensation reaction at play. So that would be our final state. Now that we have water and this is all happening, it doesn't necessarily have to happen in aqueous solution, but even whether it is or it isn't, this water is a very stable molecule, so it's not going to go back and attack to try to get back into this structure. Now that bond is made and this functional group is stable and the water is stable, so that's where the reaction is going to stop. If, on the other hand, we're thinking about back this transition state and it kicked off the what did we say, the ethylene glycol again, I mean, no harm, no foul, right? That just pushes us back through the reaction to where we began. And we know that all of these things are existing anyways as in equilibrium with each other, especially these first steps, right? But I would suggest that as soon as we do this step right here, this is going to be a step that is not nearly as reversible. These ones might go back and forth quite readily. As soon as it decides to kick off that hydroxide, we're going to go all the way to this finished product, creating water and the condensation bond. So, and every time that happens, it sticks. So think of it more like a ratchet. As soon as the reaction happens, it sticks around, and this is just going to accumulate over time, because as soon as it gets to that end state, it can't go back to where we started from. Okay, so that's the condensation reaction for polymerization, and because again this R2 also had another alcohol on the other end, and there's more structures in here with extra carboxylic acids hanging around, they're just going to alternate back and forth so that we get this terephthalic acid, ethylene glycol, terephthalic acid, ethylene glycol. So you would see this would be an alternating copolymer for one thing. Copolymer. And that polymerizes by condensation or by step polymerization. Okay. So let's have a look quickly too at what the repeating unit would be for that. So if we have, what do we do? Adipic acid and hexamethylene diamine. So that's coming up anyways, so I won't do that just now. But I want to think about what is the repeating unit on this condensation reaction. So let's actually draw those two out. Okay, so we have, let's see, doesn't really matter at this point, but we've got a length of carbons with a carboxylic acid on each end, and we'll also do, say, an amine. Okay, a diamine. So this you would see that it would repeat between the carboxylic acid one and the diamine, dicarboxylic acid, diamine, just repeating all the way through. If we add these two, if we get a reaction between these two, we're going to end up with, I want to make sure I get all the atoms correct here. Oxygen, it was, let's see, 1, 2, 3, 4, 5, 6. Okay, so 1, 2, 3, 4, 5, 6. Boop. And this is going to join directly now into the nitrogen right here. We have 1, 2, 3, 4, and back into a nitrogen. So 1, 2, 3, 4. Wait, 1, 2, 3, 4. Yep, into a nitrogen up here. H2. Okay, so So here is one new monomer link. So now we have something that has a bond here and a bond here, or a functional group on either end of it that can react with each other. So if we're looking at the repeating unit for this, we know it's going to bond through that OH, because that drops off. And this nitrogen now will only have, I didn't draw it on there, but we'll do that right now. Still has one hydrogen on it. Okay, so it still has one hydrogen. Now it's bonding through. And that's where we're going to put our repeating unit line. Okay, because this is really what's going to repeat all the way through the structure. Not just, say, this molecule, and not just this one, but it's going to be the combination of both, with one of the amide in this case, but one reaction site in between, because that's what's going to get repeated across time. And then also remember, not to forget, we also have N waters that come at the same time. So we get, say in this case, we have one A acid, okay, plus one, we're going to shorten that into HMD, going into one product, plus, and this water came out of right here, okay, H2O, so plus one water. Okay, and that is going to be the generic, obviously not the monomer names, but that's going to be the generic kind of prototypical reaction for all of these ones, because we really don't want to forget about the water in here. Unlike in addition reactions, the addition polymerization, where we didn't lose any atoms or pick up any extra atoms as it was turning into a polymer, we could just add up the molecular weight as it went through. Here you see, when we do the condensation, we have to subtract out the molecular mass, or the mass overall, of the water that we're also producing. So if we had, say these were both the same molecular weight just by coincidence, and we had a kilogram of the one plus a kilogram of the second reactant, we would not get out 2 kilograms of the product, because we have to subtract out the same amount of water, okay? Same moles of water. So here's where we might, okay, so first we're going to take this in steps. This is how you might be presented with this type of question, say in a test, if we want to work this example all the way through. So when we're looking at, and this is a really neat reaction, by the way, so nylon formation, 6,6 nylon. Why do we call it 6,6? Because we got 6 carbons over here, and we'll have 1, 2, 3, 4, 5, 6 carbons on the adipic acid, as well as the hexamethylene diamine. So that's just counting the carbons of the 2 constituents. So 6,6 nylon formation by a condensation reaction. And if you can look this up just in a different YouTube video somewhere, it's really neat, because if we have, say, a beaker here, and we put in, say, a certain amount of, and I can't remember which one it is, but let's just say the amine, the diamine first, and then the adipic acid. Whichever one is less dense is going to sit on top, but these two don't mix. They just sit right on top of each other. And right in between, let's use the colorful pen for this one. Right in between, you get a layer where the 2 chemicals meet. And they only meet at that layer. So if you go in with, say, with a hook or with anything that can kind of extract it, and you end up, okay, this is going to be my hook, and we pull up just from that layer strands of nylon that are only just forming right on the surface there, and it almost looks like a Spider-Man web kind of thing just coming out. You can imagine that that process kind of like two different things, like an epoxy coming together to form a polymer that's much stronger than each of the 2, and much longer, of course, than each of the 2 molecules independently. It really is neat. It's neat to try it. You should try it sometime, maybe if we ever get back into the lab. Okay, so if we want to look at this thing and how they're going to join up, okay, first step, remember that we would be considering the resonance structure in which we have a negatively charged oxygen and a positive charge on the carbon. And this nitrogen has the 2 hydrogens bonded to it, as well as the rest of the chain. And it also has 2 electrons in a lone pair. So that's going to be our source of electron density that form a bond across to the carbon. So what do we have? After that, we would have, okay, this is going to be R1 now. This will be R2, just so again, I don't have to write the whole thing down. So we'll have R1. I guess I should keep that consistent with what we did before. So R1 is now bonded to the nitrogen with we haven't lost any of the hydrogens yet, right? So it's going to be bonded across to this carbon right here. This is the bond we're just making. That is now bonded onto its OH group, as well as a singly bonded, negatively charged oxygen, and then through to the rest of its molecule. Okay, so let's look for charges on here. So now we've made a bond across from this nitrogen. So it is going to have the positive charge. There's the negative charge on its extra lone pairs. So again, one of these is going to now form or back form the double bond to the carbon. Again, if we just pushed off this bond we just made, we'd be back at square one. So instead of that bond getting relieved, because we can't do 5 bonds on a carbon, one of them has to go, we'll again kick out this hydroxide group to make, so this will be R1. Now we've got the nitrogen, hydrogen, hydrogen, still bonded to the carbon, which is now double bonded to an oxygen, R2. And also we've made a hydroxide, right? And that has the negative charge. The positive charge is still on the nitrogen, but again, it's going to be more electronegative. So say this bond to the hydrogen is going to be pulled away back into a lone pair on the nitrogen, leaving that hydrogen now susceptible for the hydroxide to react with it. It's going to be very acidic on this bond right here. And this is obviously a strong base, so these are going to come together. And we are left with, I say it's acidic because that hydrogen is quite loosely held. And that's how we defined these protic acids in the first place, right? So, okay, so now we have R1, nitrogen with its single hydrogen still, bonded to the carbon with a double bonded oxygen, and on to the rest. Okay, so that's the formation of the bond, and we also can't forget, we've also made water, okay? And that's all of the product together from these 2 molecules. Okay, so that's a single reaction. If we wanted to make sure, or just to show that that's going to continue, we would also have to write out the repeating unit. So in this case, we're going to have our nitrogen with the 1 hydrogen because the other one's going to be bonded out onto the next door neighbor molecule. And we can write it the same way that's up there. 6 onto a nitrogen with a hydrogen bonded to the carbon, double bonded oxygen through CH2 4. This looks more like a C than a bracket, so I'll just repair that. Okay, up into this should have been a carbon and an oxygen, and then this bond here is going to then be the bond that connects to the next nitrogen. So we'll just call that going off of the off screen. and it's going to have just a large number, n repeating units. But that would be our single repeating unit for 6,6 nylon. Okay, so let's look at a practical example of this. So let's say, for example, we had 1,000 grams of one of the starting materials. So this is the hexamethylene diamine reacting with the adipic acid. So this is what we just did, and we just say we have 1,000 grams or a kilogram of it. We want to react it with the adipic acid, and we want to know how much do we need in order to react all of that starting material, that full kilogram, and how much nylon are we going to get out of it in the end, which is a perfectly reasonable answer. So we'll just write down the balanced reaction one more time. So just say 1 mole of, say, the HMD plus 1 mole of the adipic acid. This is going to go into 1 mole of 6,6 nylon plus 1 mole of water. Okay, just we'll write that down so that we remember. The rest of this question, honestly, I think that you should pause the video here if you're watching along as we're filling out the thing. Give it a try. Most of this question is nothing that you haven't seen before. This is a very straightforward. Forget that we're doing a polymerization. Just think of it as any other reaction that we've done so far, where we have 1 mole of one reactant plus another mole of a different reactant produces 1 mole of a product and 1 mole of water. And that's it. The rest of the question you should be able to do, because what do you need to do to move 1,000 grams into moles? Well, you're going to need the molecular weight of this molecule, right? Which only depends on what atoms are in it. There it is on your page. Same thing with the other reactant. You're going to need to know its molecular weight, because we're going to get this is going to transfer or correspond to a certain number of moles of the HMD, which will have the same number of moles of the adipic acid in order to react with it, because it's just 1 to 1. And you'll need to convert that back into grams, because we want to know how much is needed. Okay, and then how much nylon is produced? Well, it's going to be the same moles of that. The only kind of, not tricky bit, but maybe thing that you would want to think about is how are we going to account for the water and the molecular weight of the nylon. So you could potentially get the molecular weight of the repeating unit. That's perfectly fine. That would work for you. You could sum the molecular weight of both of these two reactants and subtract the molecular weight of water, because that's exactly what we're doing. We're subtracting out water to get the molecular weight of this entire repeating unit. Or you could just calculate the mass for the whole thing and just subtract the molecular mass of the water, or the mass of the water that you produced. So that's how we're going to try it. So if you haven't tried it already, I say hit pause here. I'm going to carry on, and you can just pick up the video where we leave off here. So if we start, we want to get, first of all, the molecular mass of the HMD. Obviously, we're going to be doing our testing remotely now. I can't stop you from just looking this up online. I'd think that you should maybe verify it. But you know how to do that. So we have 6 carbons, 16 hydrogens, and 2 nitrogens in this one. Add that all up, and you get a grand total of 116.2064 grams per mole. And for the molecular weight of the, say, adipic acid, let's just pretend that's a ACID. Okay, so still 6 carbons. I mean, that's how we defined it. Now we only have 10 hydrogens and 4 oxygens. Okay, add all that up, and you end up with 146.141 grams per mole. Okay, so we know the amount of the reactant of the HMD, so we'll start with that. So how many moles is that? 1,000 grams. We want to get it into moles, so we have per 1 mole, 116.2064 grams. So 1,000 divided by 116 and change gets us 8.605 moles of the HMD. Okay, and now we can use our balanced reaction to say, okay, well, we have 1 mole of the HMD. We also need 1 mole of the adipic acid. So if we have 8.605 moles of the HMD, we're going to need 8.605 moles of the adipic acid. So how much does that weigh? That's what we're asking. 8.605 moles times, now we want to get rid of the mole, per mole, and we said that this was 146.141 grams per mole, and that equals 1258 grams of adipic acid. Okay, and there's your answer for the first part of the question. So that that's going to react fully to make the nylon out of the 1,000 grams of HMD. Okay, so how much nylon do we get produced here? So if we have 1,000 grams of the HMD, 1,258 grams of the adipic acid. So obviously, if we have the balanced reaction, we have 8.605 HMD plus 8.605 moles of the adipic acid. These are going to combine to 8.605 moles of the nylon plus, and again, don't forget, 8.605 moles of water. Okay, so you know how many moles you're going to get of the nylon. We want to know the mass, so either you need to know the molar mass of the repeating unit, which is a bit of a beast. You could also just sum the two masses together and subtract the 18.015 grams per mole for water. Or, and this is what I would kind of prefer to do, you just use the mass. So the total product we're going to get out of this, so if we had, you know that we can't drop mass, we're not just going to, this isn't nuclear chemistry now, so we have 1,000 grams of the HMD plus 1258 grams of the adipic acid. So this necessarily, this whole side has to weigh 2258 grams, right? So how much of that is going to be water? Well, we already know the molecular weight of water, or at least it's a lot easier to figure out since we just have to add an oxygen and 2 hydrogens. So let's go with that instead and say 8.605 moles of water times, and we want to get rid of mole, so 18.015 grams. So 8.605 moles times 18.015 grams per mole gives us, I've got it written down here, 155 grams of water. So it has to be this minus 155 grams, which is water, gives us a final amount of 2,103 grams of 6,6 nylon. Okay, and if you're not convinced, do it the other ways. Look for the molar mass of the repeating unit. It should come out the same. Any way you want to tackle this is going to be fine. Don't forget, we could also ask the inverse question. We could say, okay, if I want to make this much nylon, how much of the starting materials am I going to make? I could also say something like, okay, this process produced this amount of water. How much of the product or one of the reactants did we need to get there? Really, any way that we want to tackle this question. But you see that apart from the condensation reaction itself, which is new, the basics of all this is the same kind of conservation of mass problems that we've been dealing with since the beginning of the year. Okay, so that is it. That's where we stop for organic chemistry and for the course, actually. So that was the last topic that we wanted to talk about. So I guess that's all I have to say. And thank you very much for watching again. We're going to do some more examples of these types of questions. I'm going to put on another, at least one more sample with just some more organic molecules to practice the naming conventions. I'm also going to carry on with a supplemental kind of bonus set of videos to talk about biomolecules, just in case you're interested. It has been a part of this course in the past, but we're dropping it this year. So again, that really is just if you're interested, it's not going to be tested. But I hope that you are. I hope that you stick around. And if this is where you stop watching, that's fine. Thank you very much for what was a great year up until we were annoyingly put on hold by this global pandemic. And I wish you all the very best luck on the test and on your future programming careers. Okay. Well, thanks again for watching, and I'll talk to you again really soon.